Hello everyone, we will continue our lecture series with Kalman filter. In last couple of lectures we have given some overview and some implementation formulas and things like that, how to use Kalman filter design. And also I told last lecture that we will actually derive some of these relationships to have better understanding and all that way. So, this is where we will start our derivation process, and the first thing is we will derive everything in the linear domain and continuous time domain actually. Okay. So, let us understand the theory behind that. So, first thing what we are interested in this particular lecture is Kalman filter design for linear time invariant systems in continuous time domain. So, this going back the problem statement, it turns out to be something very precisely like this. You have got a system dynamics which is x dot is Ax plus Bu plus Zw, and whereas measured output say something like Cx plus V, where W and V are noise things and W is a process noise vector and V is sensor noise sensor noise vector basically. So, there are a bunch of assumptions which will make our life much easier later, and the assumptions turns out to be something like this. See, okay, anytime you have a linear system dynamics, okay, and remember these are like time invariant system, that means A, B, C, G, all that are constant matrices actually. Okay. And then anytime you have a dynamic equation, we also have initial condition associated with that. Okay. So, the initial condition that is x of 0 is assumed to be this way, this is x tilde 0 comma p 0. That this notation tells us the first element is the expected value mu or mean value, and this is nothing but the covariance matrix actually. Okay. So, x of 0 has a non-zero mu obviously, because that is where you expect things to be happening in the beginning, and it also has something like a noise covariance error covariance matrix P naught actually. What about W and V? W and V are expected to be, they are characterized as 0 mean. So, both of them has 0 mean, and W has Q as something like process noise covariance. So, that is how it is, Q is defined, and V the covariance is R actually. Okay. What do you mean by that? Obviously, you mean something like this. Okay, that means the expected value of W transpose, if you take that way, this turns out to be at Q times the direct delta function, and similarly expected value of V transpose, if you take, that turns out to be a direct delta function multiplied by R actually. Okay. But there is a very important behavior here. Okay, there are two assumptions actually, which tells us that x of 0, Wt and Vt are actually mutually orthogonal. That I take any combination x of 0 and W or W to V or V to x 0, I take any combination, they are mutually orthogonal. Okay. And second thing is this W and V are uncorrelated, and they are white noise. So, you see the assumptions actually, many assumptions involved, but beauty is the filtering still works actually. Okay. Understand? To summarize again, you have got three things which randomly varying: initial condition W and V, they are characterized by something like their mean value and covariance matrix everywhere. All these three signals are assumed to be mutually orthogonal, and W of t, V of t are actually uncorrelated white noise. Okay. This is these two are very important assumptions which you will use in the derivation process actually. Now, let us see how do you propose something like a filter dynamics, and how do you kind of compute the gain associated with that. That is the thing actually. That is the objective. That means, our problem statement in objective sense is something like this. Our main objective is to obtain an estimate of the state vector x hat of t using the system dynamics as well as sequence of measurements as accurate as possible. Okay. So, we do not really know x actually, remember we typically know y. So, we want to get x, obviously you cannot get x as it is. So, we get some approximate value of x, that is what we are talking about as estimation process, and the question is can you make sure that the error between x hat and the true x goes to 0 basically, then you will get x hat which closely resembles x basically. So, this is the process that we are interested in getting some x hat of t, okay, and in the process we will use system dynamics as well as sequence of measurements, and then we will get some estimate x hat of t, okay, in the sense that the error between x and x hat, if I define x tilde as that, then it goes to 0 as t goes to infinity. Okay. Initially they will have some error, but as time evolves this error will not be there basically. This means x hat will closely mimic or closely resemble x actually. Okay. What is helping us in doing that? Two things, one is the system dynamics and the other one is system dynamics, the other one is measured output. Okay. Alright, so let us see how it is possible. Okay. First thing is we propose an observer dynamics or sometimes a estimator dynamics or filter dynamics, people call it in different names and all that way. So, this is defined very close to what we already have here. X hat dot is Ax hat plus Bu plus Ke times innovation y minus y hat, and y is the actual measured output and y hat, okay, what is y hat? Now, y hat is expected value of y basically, okay, and y is nothing but Cx plus V. Okay, so, you can substitute that Cx plus V, but again expected value is a linear operator. So, we can do this linear operation here, expected value of Cx plus expected value of V, but expected value of V is 0 because that is 0 mean white noise, okay, mean is 0. It is gone, then it is again expected value is a linear operator. So, it turns out to be C times Cx, and E of x is x hat actually. Okay. So, Ke, okay, what is happening here is nothing but the gain actually. So, estimator, filter or Kalman gain. Now, the whole point is how to design this Ke. Okay. Once we know this Ke, we have got this initial condition, at least the mean value sense, and we can simply propagate this dynamics. That is the whole idea here. But you have to design a Ke in such a way that this happens, that means error goes to 0 as t goes to infinity. That is the primary objective actually. How to design that? So, we define the error, x tilde is x minus x hat, and the error, then we talk about something like an error dynamics, how the error propagates with time. Okay. So, x tilde dot is nothing but x dot minus x hat dot, simply from this definition, and then x dot, okay, is nothing but this fellow x plus Bu plus Gw, whereas x hat dot is nothing but the observer dynamics, and observer dynamics is that. You put that. Then we combine terms. So, Ax minus Ax hat. So, that comes here, Gw comes here, Bu, well, this Bu gets cancelled out. Okay. Okay. Then you get okay, minus Ke times Gw is Gw here, then minus Ke times y is nothing but Cx plus V minus y hat is nothing but Cx hat, we just derived that actually. Okay, so, this Cx hat. So, this term is nothing but x tilde, so this is A times x tilde here, and then minus Ke times this well, let us say this term, this is Gw minus Kev here, okay. Then you have got these two terms, you can combine x minus x hat is x tilde. So, that is Ke times C times x minus x tilde, that is x minus x hat, that is x tilde basically. So, you have got Ax tilde coming from here, Gw minus Kev goes there, and whatever remains Ke times C into x minus x hat, which is x tilde, comes here. Okay. Alright, so then we can combine these two guys, okay, and because x tilde is here, x tilde is here, so you take common out of that becomes x tilde here, and left out with that term actually, okay. And this particular thing I can define it as something like A0, okay, then it turns out to be x tilde dot is nothing but A0 x tilde plus this quantity Gw minus Kev. Okay. So, what happens here? The interesting observation here is the error dynamics is now driven by both process noise and sensor noise. Okay. the dynamics, when the true dynamics is actually driven by process noise, but the moment you put a filter in the loop, something like this, and then talk about error, then the error dynamics is nothing but a function of both W and V. That means, it is a function of both process noise as well as sensor noise. Now, some useful observation here, that if you talk about expected value of x tilde dot, then what happens? We take this expression and then put expected value, and then expected value is a linear operator. So, we can do all that, and it turns out that this G is a constant matrix, K is a constant matrix and all that. So, if you see G is a constant matrix, K is a constant matrix, it will come out expected value is a linear operator again, and then this one and that one turns out to be 0. These two expected value of W and V 0, they are 0 mean actually. So, 0 mean means expected value of them are 0. So, this turns out that the dynamics expected in the expected sense, expected value sense, dy dt of expected value of x tilde is nothing but a naught times expected expected value of x tilde. That means, E of x tilde, that means expected value of x tilde is a deterministic time varying quantity now. A naught, remember, that is defined as a minus kc. So, that is deterministic, and expected value is a mean value. So, that is a deterministic operator actually. I mean, once you operate expected value, the result turns out to be a mean value number basically. So, when you talk about the expected value of the error and then its dynamics, dy dt of that, this governs something like that. So, what it tells us, the expected value of x tilde is a deterministic time varying quantity basically. Now, it turns out that this a naught, which is defined as a minus k c, is stable. That means, all eigenvalues are in the left half plane. Then what happens? Expected value of x tilde is nothing but, if you take a solution of that, is nothing but e to the power a naught t times x 0 tilde, and that will go to 0 basically, because this matrix is always, or it is a stable matrix actually. So, if it happens that way, then it is said to be, the estimate is said to be unbiased, because the expected value ultimately go to 0. But if it does not happen, that means expected value of x tilde does not go to 0, then it is said to be biased actually. So, it will ultimately result in some sort of a biased estimate, which is not really good, because the error thing should go to 0 basically, then you get what is the true value in the other sense. Alright, so now we will constitute this, going back to this, we will construct this Kalman filter slowly, and first thing to see that this aerodynamics is given by something like this. Then how do you use it actually? So, we ultimately need some of these expressions later, we will see that these expressions are needed actually. So, we will go slowly actually that way. Tell first thing is, what is the solution of that? The solution of, for getting a solution, you can think, this part is nothing but a time varying input. It is randomly varying, but this is still a number basically. So, still it goes to the dynamics and then tries to alter it. So, it is a time varying input, if you see that way. And once you know this is a time varying input, the solution turns out to be like that from linear systems theory. So, this part is e to the power n naught t times x tilde dot, so homogeneous part, plus forcing function part, which is given something like a convolution integral basically, e to the power a naught times t minus tau multiplied by all these actually and d tau. Alright, so this is the solution of that, considering this as something like a time varying input. So, how do you simplify this? Obviously, these two can be separated out first, this GW and KEV part of it, and then we are interested in this RWX tilde basically, and here we will use this property that these guys are mutually orthogonal, all these signals are actually mutually orthogonal. So, when you compute, when you attempt to compute RWX tilde, then I say nothing but expected value of this fellow, and x tilde is just derived, and that is the reason why we wanted to derive that actually by the way. So, we put this x tilde expression, alright. So, we put that, because remember, if I take this fellow, then using this linear properties of expected value, and because these are orthogonal to each other and all, that will cancel out. So, what will remain is only the integral part coming out of here, and then we'll keep only that part actually, because when you operate it with W, okay, only W part will remain. Remember, W and V are also mutually orthogonal, that part will also go. So, this will go because of mutual orthogonality, this will also go because of mutual orthogonality. What will remain is only that part actually. So, you put it there, okay, that only that part, and then you can tell, okay, expected value of this, nothing but transpose thing I can take inside now, but the sequence will be reversed, and this I can attempt to put it inside, because this is a integral 0 to t. So, W of t is not a function of tau really. So, I can, it's like a constant with respect to this integral. So, I can keep it inside. So, that is what is done here. W of t is taken inside. Okay. Then expected value is a linear operator, integral is also a linear operator. So, these two will commute. So, expected value can be taken inside, and remember, these things are actually not random variable, these are deterministic quantities. So, they do not have to be part of expected value. So, expected value turns out to be this, but this by definition is nothing but this q times Dirac delta function actually, right. And if there is a integral evaluation with a Dirac delta function, there is an interesting property actually, that of any integral evaluated with Dirac delta function. See, if you have a f of t, okay, and evaluated of delta t minus tau sort of thing, okay. Sorry, how do I do that actually? F of t, Dirac delta of t minus tau. Well, let me not do that way. Okay, fine. That's then the tau sort of thing. If you, well, let me not do that. This is just tau. Let's say tau, d tau. Integral is there actually. Okay. So, what happens here is okay, this is also tau by the way. Well, in general, we can do this one. This is talk about. Let's not get confused here. Okay, in general, we can talk something like this: f of x. Okay, then delta of x. This Dirac function dx a to b. Let's say. Okay, this will turn out to be simply f of a or f of b. Let's say it is half of a. Okay, if x equal to a, if x equal to a, this is something like half of f b if x equal to b. Okay. Well, I don't know why it does not work. And this will turn out to be simply f of I mean any value, okay, f of whatever that c sort of thing, if x is any value between x equal to c, where c belongs to a b strictly, a b not included. Okay. So, in other words, if the value turns out to be one of the boundary values, okay, then the integral value is just half of that, half of the value at that particular point, half of the function value at that particular point. But if it is strictly inside the interval, then it is just the function value basically. But what happens here, interestingly, if you observe it, okay, what happens here is the integral value that we are talking about is actually, okay, where are we? Here. Okay. So, here we will ended up with, and then we notice that when tau equal to t, okay, that kind of thing, then t happens to be a boundary value. Okay. So, the entire function whatever it is we are having, we can simply evaluate it t, but we have to make sure that there is a half term associated with that. Okay. So, the half q g transpose e to the power a 0 transpose, okay, and this is 0 basically. So, evaluated at tau equal to t basically. So, when talk about this one, this is e to the power 0, okay, and e to the power 0 is identity. So, that means we will end up with some value like this. Okay. I hope it is clear, because this is one of the understanding that we need to have. So, we derive the solution like this, and then tell, okay, we are interested in this operator or w x tilde. Remember, w is independent, I mean the w is mutually orthogonal with respect to x 0 tilde and v t. So, here is x 0 tilde and here is v tau and all that. So, these will ultimately go to 0. So, we are not interested in that. What will not go to 0 is only this part. So, we keep that part only. Then you use the idea that, okay, expected value is a kind of a linear operator, and this part is constant with respect to this integral, because t happens to be one of the limits. This can go inside, and then subsequently expected value can go inside the integral. Okay, then only this expected value will turn out to be, and that is nothing but a direct delta function times q. And this because this direct delta is there as integrand actually, and this integrand goes to 0 at tau equal to t, which is actually I mean it is getting evaluated at tau equal to t sort of thing. So, that is some, I mean this is a limit of the interval, and this because of that the half term will come. Okay, and this is what it is, and because it has to be evaluated at tau equal to t, which is 0, that means e to the power 0 is identity. So, we will end up with something like this actually. Okay. Okay. All right. So, this is something that or if you are still not very comfortable or something, I suggest that you see this direct delta function integral evaluation and all that. It is available in any textbooks actually, so on mathematics. Okay. So, let us talk about that actually. All right. So, this is what it is actually. Okay. Similarly, now, okay, this is one term that we got. What about the other term? Yes, r v x tilde. So, this v x tilde is again the similar procedure. Now, we have to keep the v part of it, because these two will go to 0. So, once you have v part of it and then there is a transpose there. So, take the transpose inside, and then the reverse sequence will happen, and again expected value and integrand are linear operators. So, the one can go inside. You will have this w transpose again, which is nothing but q. Again there is an integral evaluation, and that this goes to 0 at one of the boundary values. So, that half term will come. So, again this turns out to be this fellow. Okay. Sorry, then r v of x tilde will be very similar. So, remember there is a negative term here. So, this negative term will be there here, that part. So, again we take v t inside, and then this transpose inside with the reverse sequence. So, then whatever is this expected value will go inside the integral, then this part is nothing but r times direct delta really. So, because and then again this is evaluated at one of the limit points. So, half of that, and then evaluated tau equal to t, which is identity here. So, left out with that actually. Alright. So, why you are interested in so much of this analysis of these two things and all? Because we will soon need it in the error, I mean the covariance matrix propagation and things like that. We need that actually. So, what is error covariance matrix? As I told, it is defined as an outer product between the error of these variables x tilde and x tilde transpose, expected value of that. Yeah. So, what about the error dynamics or this propagation of this covariance matrix? What happens actually? Okay, so, then that is p dot, and remember derivative and expected value both are linear operators. So, derivative can go inside the expected operator, and you have two variables like this. So, it operates that way, and remember these are vector matrix things. So, make sure that the order is maintained. And then this part I will keep it as it is, but what about this? This is nothing but this I mean what if I alter these two, then the whole transpose actually, and I take expected value inside. It turns out that it is nothing but expected value of this plus expected value of the same thing whole transpose actually. Okay. So, if I get expected value of this, I do not have to recompute it, because this is nothing but this same thing with a transpose thing. Now, what about this fellow? Okay. So, expected value of x tilde transpose, what is that actually? Okay. So, now x tilde dot is nothing but this one, right, we derived it before, and so we just take this one. Okay, a lot of simple bookkeeping actually. So, then you multiply, expand the bracket, multiply everywhere, then take expected value. Okay. And remember this this what expected value what you are seeing here is nothing but r w x tilde, and this expected value what you see is nothing but r v x. That is why we are interested in deriving that. Then this by definition is simply p. Okay. So, what it turns out to be this one is nothing but n naught p plus this quantity which we derived to be g times this quantity, and this quantity has been derived like this, y naught k times r v x tilde, and r v x tilde derived something like this. Okay. So, then it if you expand that, it turns out to be n naught p plus half g q g transpose plus this minus becomes half of k e r k e transpose basically. Okay. Then what is p dot? Remember, p dot is expected value of this plus same thing whole transpose. So, we got expected value of this. So, then p dot is expected this one plus the entire thing whole transpose actually. Okay. So, p dot turns out to be like this. So, very close to what we know in LQR theory actually. Okay. All right. Now, we need to find a solution for p. Okay. And the theorem tells us some standard result is there, which tells us that if k is designed in such a way that a0 or a naught which is defined as a minus k. So, if this a minus k is stable, okay, k is designed in such a way that a minus k is stable, then given an initial condition for p, which is p of 0 is p naught, then a positive semi definite solution can always be obtained. That is what the theorem tells actually. Okay. And there is also another theorem which tells us that the error covariance matrix P actually approaches a steady state value P as long as this is asymptotically stable. Actually, not only there is a positive definite solution, but it actually goes to some sort of a steady state solution actually. If it is a steady state solution and we want to that particular steady state solution only, then P dot has to be 0 basically. Okay. So, this entire expression, okay, this one is nothing but p dot is 0. So, hence the entire expression is equal to 0 basically. Okay. Alright. So, in steady state the differential equation reduces to something like this. Okay. Then you have to note some comment here that p of t by definition is something like this, and hence what you mean, a smaller p of t implies better estimate basically. The error covariance matrix is smaller, the estimate is better basically. Okay. And there are also some definitions like this, which tells us that if p1 p2 are both positive semi definite, okay, and p2 minus p1 is then p1 is less than equal to p2, provided p2 minus p1 is a positive definite matrix. Remember why this definition sort of thing, because we are now talking about matrix algebra basically. So, you cannot compare this to whenever you have this p1 and p2 two matrices, how do you compare them? Okay. And by definition it turns out that if p1 is less than equal to p2 if p2 minus p1 is a positive semi definite matrix basically. Alright, now here is a point where you can actually go ahead and try to derive Kalman filter. So, what it turns out, now so far so good actually. If you see all this, our aim was to get something like a p dot, and p dot, if you see a reverse sequence sort of thing, our actually aim was to get some sort of a error covariance matrix propagation dynamic actually. So, we wanted to get a p dot, and p dot turns out to be something like this and the same value to whole transpose actually. Okay. So, then this value we are interested in. So we had to do some algebra like that, but here is a point where you get this R W x tilde and R V x tilde. So we wanted that expression actually, and that is why we derived this R V x tilde and R W x tilde that way. Okay, so now I hope it is little more clear actually. So we got this this P naught, okay, and there are some theorems which tells us there is a stable solution. If A naught is stable, then there always exists a P, a positive semi-definite P, and okay. And in general, I mean it will reach a steady state value, and once it reaches a steady state value, the equation is given something like that actually. Now, what you are interested to obtain a constant observable Kalman gain, we are not interested in time varying Ki and all that, we are interested in something like a constant Ki basically. So, if you do that, then the idea here is to minimize the steady state error covariance matrix. Okay. If you look at this one, there is a solution which is positive definite and positive semi definite at least and all that. Okay. Okay. Alright, so this is okay, so that is how it is. So what you are telling here is we are interested in a steady state value which is smaller actually. So okay, that means we are interested in minimizing the steady state covariance matrix P basically. And what is steady state covariance matrix P? The solution that comes out of this equation actually. Okay. So here is an optimization formulation which tells that okay, we have to kind of minimize this P, but remember P is a matrix now, but trace turns out to be a kind of a norm basically. So we are interested in minimizing the trace of P now. Okay. So what is P? By definition, limit t tends to infinity. This thing actually, right? That's the trace of P. What it means. Okay. Limit t tends to infinity. That's what you want to interest. So when t goes to infinity, these error quantities are there, x1 tilde square, x2 tilde square, like that actually. And expected value of all that, if you put it and sum it up, and that's what you want to minimize actually. Okay. But this has to be minimized subject to this constant equation, because this is what the constant equation we got. Okay. So this cannot be ignored actually. This has to be subject to that. So in other words, we want to find some appropriate selection of P and Ki in such a way that it will minimize the steady state P or steady trace of P to be very exact, okay, subject to this regard equation basically. Now here are some facts from matrix calculus, and this matrix calculus, I mean some facts I will buy it actually, will not go through the detail of these derivations and all, and these are all matrices actually. Remember, sigma is a matrix and we are also matrices, and some of these results are available basically. We will simply try to use it. So what it tells us, we have got this optimization problem here, where you have to minimize this cost function subject to this equation which is equal to 0. So the theory tells us that you can have an augmented cost function which is the original cost function plus this half of trace of g times s, where s is a Lagrange multiplier matrix actually. Then the necessary condition turns out that okay, all these derivatives, now these are functions of p, k, and s. So the partial derivative of j bar with respect to p has to be 0, with respect to k has to be 0, and with respect to s has to be 0. Now this partial derivative can be derived using some of these results here. Okay. So it turns out to be something like this. Now we have to solve these three equations together basically, and that is not that difficult to see. Okay. So from equation 1, okay, you can actually, if you do this, okay, then this equation can be written something like this, and this is nothing but a kind of a Lyapunov equation actually. Okay. Okay. So hence, as long as A naught is stable, S is guaranteed to be positive definite. Okay. A naught is system dynamics matrix for that particular Lyapunov equation and all that. So as long as A naught is stable, okay, there will be a positive definite matrix S which will satisfy this equation. Okay. Remember what is S? Okay. G is the equation. Okay. S is nothing but the Lagrange multiplier actually. Okay. Lagrange multiplier matrix, in to be exact. Now, once you have that, okay, let us go to this equation 2, and what does the equation 2 tells? It tells something like this. Okay, that means KER minus PC transpose is 0 because S is a positive definite matrix. It cannot be 0 actually. Okay. So, KE, okay, if you see this equation, just KE is nothing but PC transpose R inverse. And interestingly, it is exactly similar to what we have actually derived in LQ observer theory. If you can see that lecture notes, I mean the slides for that lecture, you will see that actually. So, K is nothing but PC transpose R inverse, and that is how it is, and we have used equation 1 to whatever equation 3. And so, from 3 you can put some, you can put it that way. Now, you expand A naught is A minus KEC sort of thing. So, that you expand, all that is equal to 0. Okay. And then it turns out to be something like that, AP minus this PC transpose R inverse EP, and all that actually is equal to 0. Okay. Okay. That means, okay, I mean you can see that P AP is here, okay. Then PA transpose is coming from this term, okay, KE transpose, and K is nothing but this one, PC transpose R inverse. So, you can substitute that wherever Ke appears, okay, and you will get that. Okay. Then it turns out that two terms will cancel out actually, because R inverse is identity. Once this is identity, these two terms are equal and opposite. So, they will go. So, you are left out with something like this actually. Okay. So, this turns out to be the filter algebraic Riccati equation, or in short it is called filter ARE actually. Okay. So, once you solve this, you get the Riccati matrix P, and finally, K is nothing but PC transpose R inverse. That is how it is. So, summary is something like this. You have got system model, which is x dot is x plus bu plus gw, and we have got a measured output, which is y equal to cx plus b, and you have initial condition, you have got process noise, you have got sensor noise. These are characterized by their mean values and covariance matrix. Initial condition, mean value is x tilde on v naught, and W is 0 Q and V is 0 R. Okay. Assumptions here are these two noises are white noise, and this W V and also X naught except T naught are actually mutually orthogonal. Okay. Okay. Then you define that error in the state, something x of t minus x hat of t, where x hat is the estimate of x, and our interest is to find x hat of t such that p, okay, in the limiting sense, that means steady state p, limit t tends to infinity, expected value of x tilde transpose, that is what it is. So, steady state p has to be minimized actually. So, filter operation, we initialize it first, something like x hat of 0. Then we need to solve this Riccati matrix or filter ARE, that's the equation that we need to solve. Then you can compute the Kalman gain, and then you can propagate the filter dynamics, because x hat 0 is known and this filter dynamics structure is known with a deterministic value of Ke. Okay. So, there is nothing unknown now here. Okay. So, you can propagate this filter dynamics, and because of the nature of the solution and things like that, it is guaranteed to give stable tracking, I mean stable error dynamics. That means error value, that x tilde x minus x hat will ultimately go to 0 as t goes to infinity actually. Alright. So far so good. It turns out to be very lucrative actually, but there are certain issues for successful operation of Kalman gain, and there are certain mathematical comments also basically. So, let us see those one or two actually there. So, first thing is this y minus y hat, that is you can think about that as y tilde, and y minus y hat is something y minus y hat is something like well, I should have that. Yeah, y minus y hat. So, y is actual measurement and y hat is Cx hat actually. Okay. So, estimated output, predicted output, whatever we can say actually. Okay. So, if you take actual output minus this predicted output, this is called the residual or innovation actually, okay, which is also a zero mean white noise, okay, and that actually leads to this whiteness test actually. Okay. So, in other words, if you implement a filter and then tell okay filter is working, then you also need to do some sort of a few tests to validate your result that it is actually working, and you are not misled actually. So, what the first result tells us that if you think about residual or this one, okay, so it also needs to be some sort of a zero mean white noise, okay, right. So, this what you can do now is you generate this this residual for a large number of signals and they try to find out the mean value of that, and that should go to 0 actually, okay. So, that is called whiteness test. And in other words, this particular y tilde, okay, has to behave like a white noise actually, okay, and y tilde is something like this Cx tilde v and Cx tilde plus v, okay. So, and then expected value of y tilde transpose should turn out to be r actually. So, that is actually a kind of a whiteness test basically. And also remember in the estimation process, the state equation actually helps in eliminating the outliers. Okay. That means you propagate the state equation of filter dynamics and things like that. You expect some sort of a value for y hat. You know what is y hat actually. Okay. Now, if y turns out to be pretty close to y hat, then okay, maybe you are wrong or the sensor is good. So, we can operate that. I mean, you can update the values and all that for x hat. But if for some reason some y happens to be much larger than y hat, then something is going wrong there. Okay, you tell okay that data particularly turns out to be something like an outlier. So, we do not have to use it actually. Okay. So, then it turns out that the state equation because you have to propagate to see what is Cx hat. So, the idea here is the state equation actually helps us in eliminating outliers also. It means if there is some outlier somewhere, then we do not have to operate it actually. Okay. Whereas, the measurements or other innovations help us in correcting the modeling errors or inaccuracies actually. Okay. That means it does both the things. It actually helps us in declaring some data as outlier and hence not using it, or it actually kind of if you use it because you are relying more on the sensor output and less on the system process modeling actually. So, it actually helps us correcting the modeling errors or modeling inaccuracies as well actually. So, what is the third point? Third point is if Ca is observable and this pair A comma g square root of q is reachable, then the filter ARE has a unique PDF solution, okay, for the Riccati matrix P. Okay. Moreover, the solution leads to Kalman gain that drives the aerodynamics asymptotically stable. Okay. So, there are two conditions. One is the problem has to be observable, otherwise nothing will work, your Kalman filter is also not going to work actually. So, for the Kalman filter to work, this pair Ca has to be observable first and this pair A comma g times square root of q needs to be reachable actually. Okay. And if these conditions if observability is not there, you can't do anything, but on top of observability, this has to be there for unique solution of this filter area. If it is there, then you can get something like a unique PDF solution or first definite solution of from algebraic Riccati equation or filter area equation. Okay. And moreover, this solution will ultimately lead to Kalman gain. Remember, KE is nothing but P C transpose R inverse. So, ultimately lead to Kalman gain. That drives the error dynamics asymptotically to 0 basically. Okay. Now, the fourth observation. Okay. The assumption this one A comma G times square root of Q is reachable requires that the process noise should excite all states actually. If your process noise keeps on coming and they ultimately should excite all states. Okay. And if it doesn't, then probably something goes wrong and you will not be never be able to observe it properly actually. Okay, so because there is a requirement that it should excite all states, sometimes there is a necessity now to inject artificial process noise to the plant. For example, if you talk about kinematic level and dynamic level variables, typically system dynamics contains two levels of variables, something like kinematics, which is something like x dot is V, and dynamics where V, well, where V dot is A. Now, V dot is not really A plus W, I can say that way. Okay. Okay. So, what about, because this is a physical quantity, normal acceleration, right? I mean, acceleration applied to the system basically, that is directly influenced by noise W. Okay. Now, the question is, okay, because it needs to excite all states. Now, W, suppose it does not excite X actually, it keeps on exciting V only through this V dot equation. Then it makes sense to kind of inject artificial noise W1. Remember, X dot is V simply by definition, there is no noise, nothing in that actually. But still, by putting an artificial noise W1, thinks the filter can work beautifully actually. Okay, so that's what it tells. Another point is the requirement to compute R inverse demands that R is positive definite, and hence it is necessary that the measurement noise outputs all the measurements. So, you have measurements, but R inverse has to happen because you cannot define some set of measurement and tell, okay, that particular component I do not know what is going on actually, you can tell that. So, what it happens is the requirement to compute R inverse demands that R needs to be positive definite, and hence it is necessary that the measurement of noise corrupts all measurements, and because of this there is usually some preference, there is some performance degradation, and if there are some noise free measurements, typically either you do it that way, that means you artificially inject the noise and make everything go bad, and so either you leave it that, or there are some noise free measurements or some little bit more practical complicated filters should be used. They are typically there in the literature. One thing comes from this dash filter, for example actually. So, there are bunch of issues here for successful operation of Kalman filter. We will see more on that when we finish the external Kalman filter later actually. Alright, so only then if you make sure that these things are not forgotten, these are kept in mind, then you can get nice behavior of Kalman filter actually. The another one which another important statistical property, that expected value of exterior transpose should be 0. That means the state and error vector. Okay, this is, remember, this is estimated state, this is estimated error. So, the state vector is orthogonal to the estimate of the state vector actually. Okay, you can see, understand in more details. And lastly, this comparison sort of thing. Suppose you have observer design and a filter design. That means you have this x dot is x plus b here, but there is a process noise plus w, and you have got y cx, you have got y of cx plus b here. Okay. Interestingly, the solution to both problem turns out to be same. I mean, this k equal to p c transpose R inverse. Okay. And where the p is the solution of this Rickard equation actually. Okay. But here if you talk about the other one, it is the Rickard equation contains G also, G transpose this side also actually, it's only difference there. Okay. Then this part I have already told you before, Kalman filter derivation assumes white noise, and some many real life problems are typically not dictated by white noise. Rather, color noise are very frequent. So, as an example, I told wind gust noise and all that actually. So, in that situation, one can form a subsystem whose input is a white noise and output is a color noise, and explain all that a little while before. And the subsystem is then augmented with the original system to form an augmented system whose input is a white noise actually. So, this is what it is. Initially, this okay, I showed an example already before actually. Initially, what happens is okay. So, you have got a transfer function, or you have got some sort of a small time state space model, for which you take input as white noise and output as the actual color noise that you are expecting actually. So, then what happens is you tend to kind of augment these two together, and then you will get what you really want actually. Okay. So, this example I have just given a little while before actually, or maybe in the previous lecture you can see basically. Okay, so this is very neat concept, because many times it is actually colored noise, but colored noise can be actually a dynamic model or static model. Either way actually you can think about putting that as some sort of a system dynamics associated with that colored noise is something like this. So, you have got xw dot is something like this, or n is a white noise, and where w is a colored noise, and that is a function of xw and white noise both. So, you can put that in the state space form and then carry out algebra basically. Okay. Now, if you do that, the Kalman filter theory can now be applied to the entire augmented system basically. Okay. So, then it can be addressed, and this is typically called shaping filter ideas and all that that way. So, if you see that there are a bunch of these comments out here, issues, observation, comments and all, just be aware of that. There can be many more comments, many more suggestions in the literature as well actually. And we will slowly go towards the discrete time derivation. And then how do you put continuous time, discrete time together? That means system dynamics can be continuous, but measurements are discrete. So, how do you do that? Finally, we will extend the same concept in the same discrete time, discrete continuous setting for extended Kalman filter, which is very heavily used, and with lot of applications. And then there also we will talk some of these issues and recommendations and things like that actually. All right, that's all I want to talk here. Thank you. Bye.